Welcome back to Rice.AI Code Room. Today we are tackling LeetCode 3655, XOR after range multiplication queries 2. Let's explain the problem. We are given an array of numbers and multiple queries. Each query consists of a starting index L, an ending index R, a step size k, and a multiplier v. We must multiply the elements starting from index L, jumping by k until we reach R, by the multiplier v, modulo 10 to the 9th power plus 7. Finally, we need to return the bitwise XOR of the entire array. In our example, the multiplier is 4 and step is 1, so every element becomes 4, resulting in an XOR of 4. If we process each query naively, the worst case is taking a step of size 1 across the entire array, which takes O of n time per query. With Q queries, the total time complexity would be O of Q times n. Since n and q can both be up to 100,000, this requires 10 billion operations, resulting in a time limit exceeded. We need a way to optimize this. To optimize, we use a technique called square root decomposition. We choose a threshold b, typically the square root of n. We then split our logic into two scenarios. When the step size is large, meaning k is greater than or equal to b, the number of elements we actually touch is small. We make it most n divided by b jumps. Because this number is small, we can just iterate through the indices and multiply the values directly. When the step is small, meaning k is less than b, we might touch up to n elements, which is too slow. Instead, we defer the updates using a multiplicative difference array. Rather than multiplying every kth element immediately, we record a multiplication by v at the starting index L, and a multiplication by the modular inverse of v right after the ending index R. We process all these deferred updates later. Let's dive into the implementation. For our large steps where k is greater than or equal to b, we simply run a loop from L to R, jumping by k. At each step, we update the direct array with the multiplier v modulo 10 to the 9th plus 7. This direct array holds the accumulated multipliers for all large steps. For the small steps, we compute R prime, which is the last index we actually touch before exceeding R. We then multiply our difference array at step size k and index L by v. To stop the effect from bleeding past our range, we multiply the difference array at R prime plus k by the modular inverse of v. This cleanly isolates our multiplication range. After all queries are recorded, we need to apply the small step difference arrays. For each small step size k from 1 up to b-1, we iterate through the array from left to right. We propagate the multiplier by multiplying the current position by the value located k steps behind it. This sweeps the multiplier across the array correctly. Finally, we combine everything. We iterate through every index of our original array. We start with the large step multiplier from the direct array, then multiply it by all the small step multipliers from our difference arrays. We apply this total multiplier to the original number, and compute the running XOR to get our final answer. To wrap up, let's analyze the complexity. The time complexity is O of Q times square root of n for processing the queries, plus north times square root of n for propagating the small step updates. The space complexity is O of north times square root of n, as we allocate a 2D array for the small step difference logic. Thank you for watching.